This is lecture 3 of my cardiovascular lectures. So if you haven't watched all parts of lectures 1 and 2, I advise you to do that. This is the first part of lecture 3. So in lecture 3, we're going to cover various topics. We're going to cover blood pressure and resistance to blood flow. And that's basically what we call hemodynamics. And in this part of the lecture today, we're really going to talk about blood pressure and its measurement. In part 2 of this lecture, we'll talk about control of blood vessel diameter and total peripheral resistance and its effects on control of blood pressure. And then finally, in part 3, we'll talk about control of blood pressure via physiological mechanisms. To focus on what I'm teaching today can be found in chapter 30 of Pocock and Richard's Human Physiology. So let's start talking about the basic physiology, the physics, if you like, of pressure and flow. Now, blood flow is determined by the perfusion pressure. That's the pressure driving flow, because fluids will flow from high pressure to low pressure. If you remember, blood vessels leaving the heart in the arterial system at high pressure, veins are at low pressure. So that's the driving force, the perfusion pressure. But that's also coupled to the vascular resistance. That's the resistance of the tubes, the circulatory system to blood flow. So think about a hose pipe. The amount of flow is determined by the resistance of the pipe to flow. The wider that pipe, the more flow that you get. The more constricted that pipe, then you might get increased velocity of flow, but it's under much higher pressure. So as I said, perfusion pressure is the difference in the pressure between arteries and veins. And an increase in the perfusion pressure, in other words, an increase in the pressure within the system, causes an increase in flow. So it's the blood vessels themselves that offer the resistance to the flow, and that is the vascular resistance. So increases in vascular resistance and the flow will fall. So if you constrict the blood vessels, you constrict the amount of flow that can occur. Now, it's worth bearing in mind that we have a pump in our circulatory system, and that pump, if you remember, is contracting and relaxing. Yeah, so it's for the whole circulation, blood flow is normally dictated by the difference between the arterial and the venous pressure, but bearing in mind that the arterial pressure will vary from high to a little bit lower during the cardiac cycle. But it will still maintain an overall flow from the arterial system to the veins based on that pressure difference. The other thing to bear in mind is that vascular resistance depends upon the radius of the blood vessels. In other words, the diameter of the blood vessels, or the radius of the blood vessels, and as well as the viscosity of blood. And because the viscosity of blood doesn't usually change under normal health, it's really the radius of blood vessels which is determining the vascular resistance. And this follows what's called Purcell's law, which might be familiar to anyone who studied physics before, but it's really important here. You can also look at Pocock and Richard's on page 461 for a description of Purcell's law. Now this is important because resistance is dependent on the fourth power of the radius. And what that means is if there's a very small change in the radius, then there's a huge change in flow. And again, if a small change in diameter of a blood vessel will massively increase the amount of flow. And this brings us to a little bit more physics. We think about laminar and turbulent flow. Now, Purcell's law, which I've just mentioned, assumes that you have a situation with laminar flow. Okay, and that is the condition that is normally occurring in the body as well. Normally the blood flow is what we term as laminar in flow. Now, turbulence can also occur if there's an obstruction in the direction of flow. And turbulence occurs when a blood vessel becomes distorted or has some kind of obstruction with inside. So, for example, that could occur where you have a disease such as atherosclerosis, where you have an atherosclerotic plaque forming in the artery, which could cause turbulent flow at those sites. And that's bad news normally for your health. And this turbulent flow, if it allowed to continue, can actually contribute to thrombus formation. Dr. Black will talk about that, and Dr. Bayapuri will talk about it next year. However, this turbulent flow can also occur if an artery is clamped. So if you placed a clamp on an artery to reduce the amount of flow, then you would induce turbulent flow. And we can exploit that in the measurement of blood pressure, because turbulent flow makes a sound that we can listen to. And that will be covered in the blood pressure workshop, but some of the information I'll mention now is really important to help understand that workshop. Okay, so this is back to a graph that I've previously shown, and it's showing just the pressure across the cardiovascular system. Here, if we look at the pressure in the ventricles, and we can see the pressure in the ventricles varies wildly from very low pressure during diastole to very high pressure during systole when the heart is contracting. Then if we move into the arterial system, you can see that that flow continues, but it is dampened out. And while it still raises between very high and very low, there is a net, or the average pressure is much greater in the arterial system than it is in the venous system, where it is being returned to the heart. And this creates flow across the cardiovascular system, but this pressure wave that we see in the arterial system can be felt as your pulse as well. So it causes a pulse because there's a change in the pressure in the arterial system. Now, what's key here in terms of regulation of blood flow and blood pressure is that the largest drop in pressure occurs across the arterial system. These are the large arteries down to the arterioles and the capillaries, and we can see this huge drop in pressure as we go down the vascular tree. Therefore, because we have this largest drop in pressure, it is the vascular resistance in the arterial system which controls the overall peripheral resistance and therefore controls blood pressure. And the easy way to think about this here is that if, and I will just switch to a pen to illustrate what I mean. If we look at this diagram, and if we were to change the diameter of the arterioles down here so that they were more constricted, then that would increase the pressure within the arterioles. So we'd get a curve that looked maybe like this now. So hopefully that makes sense. Now, if you were to clamp, and I'll use a different color, if we were to clamp the veins, we would get an increase in resistance in the veins, but they're already at very low pressure. So we'd get virtually no change in the blood pressure overall. Hopefully that makes sense. So when we clamp the arterial pressure, we get a huge increase in the overall pressure, but virtually no change in the arterial system. Thus, Thus, that's why it's the arterial system that controls the peripheral resistance. So now this brings us to how do we actually measure blood pressure? Well, you can do it directly, and normally I would aspirin some interaction here, but you can place cannula directly into a blood vessel. But that would involve surgery. You'd have to open an artery and place a pressure device directly into the blood vessel. That is extremely invasive and will probably, just to find out what the blood pressure is, will probably end up killing lots of people in that process. So it's not ideal, but is occasionally done during some forms of surgery. What we tend to use is a method, or the traditional method is called auscultation. Now there's various mechanisms of auscultation, but this is the one that I'm going to describe here. The blood pressure practical will tell you how blood pressure is actually measured. Now what was noted many years ago was that when you have turbulent blood flow, it creates sounds. So you can use a device called a sphygmomanometer. A sphygmomanometer is a pressure cuff attached to a pressure cuff, and a stethoscope to listen to the sounds of turbulent flow. And again, in the practical, you will listen to some of these sounds that you can be heard, which are called Korotkoff sounds. So when blood is flowing normally in laminar flow, you don't hear anything. But when you inflate this pressure cuff and clamp the artery within the arm, that will then induce turbulent flow that you can begin to hear. And these sounds, and listening to what's happening to these sounds, allows us to record the blood pressure. Now, how this works is that your normal blood flow is not making any noise at all. Okay, but if we inflate this pressure cuff to a pressure higher than your blood pressure, what we get is we cut off the blood flow to the arm altogether. Okay, so that's essentially what's happening when we're inflating that cuff of the blood pressure monitor. What's shown in this diagram is the systolic and diastolic pressure, and shown in red is where some blood flow is occurring. So if we were to inflate this cuff to above the normal blood pressure, what would happen is we've completely stopped the blood flow. Then, as we slowly reduce the pressure in the cuff, what begins to happen is that some blood flow returns. Now, if you imagine if you were to take a hose and put your hand over the edge of it so that nothing could flow, and then you slowly release the small amount, what you get is a small jet of water under high pressure that would be turbulent in nature, and that makes a noise against the wall of the artery, and that's what we can listen to. That's the first Korotkoff sound. And as we continue to drop the pressure, we get more blood beginning to flow, and that sound begins to get a bit louder. And then as more blood flow returns, that sound begins to get quieter because the flow is less turbulent. And then as the pressure in the cuff drops below the systolic blood pressure, the noises suddenly disappear. So what we can do is we can listen to that first sound, or as some of the electronic devices do, listen to the first vibration. And where that first begins to occur, that's what we call systolic blood pressure, because the pressure that's read in the cuff will be the same as the highest pressure in your blood vessels. As the blood pressure drops and then the sound disappears, or the vibrations disappear, then where that occurs we call is the diastolic blood pressure. So that's the two measurements of blood pressure. And that brings us to the idea of normal blood pressure. And I'll go over this in much more detail next year, talking about this related to the disease. But generally, we consider normal blood pressure to be a systolic blood pressure of less than 120 millimeters of mercury and a diastolic pressure of being less than 80 millimeters of mercury. And the blood pressure values I'm looking at here are based on what would be measured in a doctor's surgery or in the clinic. If you measure blood pressure at home, it's much likely that your blood pressure will be slightly lower because it's a less stressful situation. The other important thing is that there's not really any such thing as normal blood pressure, because blood pressure will depend on your age, your body size, and also your biological sex. So men tend to have higher blood pressure than the women. If you could imagine a 6-foot, highly muscular male, it's probably going to have a very different blood pressure to a 5-foot tall, slender woman. Okay, and it's worth bearing in mind that this normal is based on a young Caucasian male, as so many things are. So it's worth bearing in mind that a little deviance from this normal blood pressure is quite normal. What we're often interested in clinically is high blood pressure, and what's dictated as high blood pressure is systolic blood pressure over 140 millimeters of mercury, or diastolic blood pressure over 90 millimeters of mercury. And if your blood pressure is above these values, no matter what your ethnic background or your size or your biological sex, that would be classed as high blood pressure and makes you at higher risk of cardiovascular diseases. And problems associated with high blood pressure will be covered in PM2C2 next year. And it's worth bearing in mind that blood pressure is the largest and most predictive risk factor for other cardiovascular diseases, and is a cardiovascular disease in its own right.